Okay, so I think all of your final project teams are formed. There are a couple that I had to manually kind of move people around, but you should all know about which groups are which. If you've received email from me, if you did have a group that had to be kind of manually formed, make sure that you go and submit that final project team member name with your updated finalized group, and then you'll get credit for that assignment. So it'll remain open. But just make sure you submit those new names so that it's clear to everybody who's on your team, and then being able to move forward from there. So with that in mind, there's no formal lab this week. So instead, now that you've formed your lab groups, we provide you that time to try to put together this input modeling report, which is due this week in place of a lab report. So there's information online on what is expected of the input modeling report. The biggest thing here is I want you to identify the system that you're going to study and the kind of general reason why you're studying that system. Like if you noticed long lines, or does it seem like there's opportunities for optimizing something for efficiency and so on, and then describe the input models that you'll likely need, describe the output variables that you'll likely take in order to measure performance, and then show me some evidence that you have access to the system by gathering data on one of those input models and then fitting a model to it, similar to what you did in Lab 8. Not looking for all of your input models, just looking for some evidence that you have access to the system, so that after this input modeling report, I can just be hands off until the last week of classes when you upload your presentations and your report. Any questions? Okay. Otherwise, then next week and the week after that, Lab 9 and Lab 10. So in Lab 8, you were introduced to the input analyzer, so that helps you fit these data sets. Lab 9, there is a kind of basic statistics tool that's built into the arena called the output analyzer. It's not as clean and the outputs aren't as polished as a true stats tool, but for quick and dirty comparisons of model outputs, then it provides you some of help with that. And then in Lab 10, there's some advanced topics, and Lab 10 is actually structured so it's sort of like two labs in one, in terms of it's got bonus added onto it. So if you just do sort of the normal length lab, then you get lab credit. But then there's like additional topics that I think would be great for you to learn about. And so I've sort of tried to incentivize that through some extra bonus there. So Lab 10 then allows you to learn not only about certain tools like OptQuest and things, but also about batching. So returning to one of our first labs, when you did the muffin sim by hand, we kind of saw, a brief introduction to batching. Now we'll actually see how batching works in Lab 10. So hopefully those are things that can help you in building your models for your final project. I started to get emails about, would this be sufficient for my final project? And the key idea, we used to use this rule that you'd want to make sure you're using an arena model that is complex enough that you would feel the urge to use a submodel. And so if you look at some of the samples that I provided from previous semesters in the final project folder in their module on Canvas, then you can see some examples of how complex the models that students usually submit are. And so once upon a time, it used this rule where we'd say, well, you'd want to build it so that there'd be kind of an obvious subsystem where it would make the most sense to present your model. If you, in Arena, you can highlight any one of those subsystems and you can kind of right click on that group and say, make submodel, and it'll replace it with a block. And then you can drill into that block and see your subsystem. But then the main view of your main system is just that's going to be replaced with just that block. And so the original thought was, well, it needs to be sort of complex enough that it makes sense to do that. So if you just have 3 blocks in a row, it doesn't really make sense to do that. But if you have kind of complex logic, that we refer to this as like, all of these different things that could happen to a customer before they enter a restaurant, then maybe that entry logic that has all these forks and branches and things like that, maybe that could be sort of a submodule. But the kind of, but that rule didn't always work. And so, I mean, generally what I'm trying to say is you want the sim model to or the whole project really to address a problem that you need sim to be able to understand. So if you give me a project where you're like, well, we're going to model this particular restaurant as a single channel, single server queue. And so we're going to have inputs and we're going to have service times and we're going to see what happens if you decrease the service times. Well, we already know what's going to happen there. So, if you have people coming in and they're waiting on a server and the time in that server is what causes people to wait. If you make it spend less time in that server, the server is faster, then people wait less time and then there's shorter queues. We already know that. And so that's not something we need to simulate. And, simulation might be kind of a demonstration, but it wouldn't really help us analyze it. Now, if instead you'd said, well, I've got this bank and it's got a number of tellers, and they're human tellers, and the bank is considering adding kiosks. And there are trade-offs to when you add these kiosks. Because if you add a kiosk, it's going to take up a window, so you're going to get rid of a human teller. But it's going to reduce the cost of running the bank because you don't have to employ a human. But if everybody goes to the kiosk, then has to escalate to a human, then now you've actually made things worse. And so there's this potential that things could go worse or get better. So that's a lot of times what these projects will be, is that the students will pick a relatively simple, given we only have a couple weeks, system to build as an as-is system, and then come up with an intervention to say, we're going to add, like I said, kiosks or something like that. And we're going to try to build a model of what that might look like. And then we're going to compare the performance of those two. And it won't be obvious ahead of time which one's definitely going to be better. Or we'll maybe try to analyze, if you manage to achieve these stats with this new kiosk system you installed, like if the kiosks manage to be this much faster, or if there's this much cheaper or so on, then maybe in that regime, you end up doing better. But if the kiosks are a little slower and so on than this other regime, the kiosks are worse. So it kind of depends on the performance of the kiosks. And that's like a nice result too, because you may not know what it's like to put a kiosk in a bank. You don't have data on that. So then you just have to think, well, a hypothetical kiosk, you could say, well, I can imagine a universe where kiosks behave this way or behave that way. And then you could say, well, under which, like maybe under both conditions, you're better off than the state of the art. And then in that case, install the kiosks. But if instead you find out that you're only better than the state of the art under this one kiosk condition, then you would make the recommendation. If you could achieve, kiosks that have these performance measures, then we would recommend you install the kiosks. So something that, again, is not obvious until you run the sim. That's the level of complexity we're looking for. But when I look at these input modeling reports, if things looked overly ambitious, I'll probably tell you that you don't have to go that far. You only have a couple of weeks to build this thing. So it's sort of a balance there. Not too complicated, but it can't be something, if you just stare at it, it's obvious what the results are going to be even before you run the sim. All right, so any questions about that? Okay. And then after lab 10, then the rest of the lab times you can spend, view that effort that week on finalizing your final project. So the final project, input modeling report, that's the next one here. This is a group submission. Only one team member has to upload that. It's due Sunday, just like any other lab report. I could have made it due a week later, but I want to make sure that I have enough time to read them and provide you feedback back to say, well, maybe make it a little more complex here, maybe a little less, and so on. Again, it's okay if you don't capture all of your inputs, just one is fine. Just need to demonstrate you have access to your system, and details about the desired format and content are posted on Canvas. This is not a long report. It should be a lot shorter than your normal lab reports, or roughly, I think it's like 2 pages or something like that at max. So I'm not looking for a lot. I just am going to see that, okay, you've selected a system. It makes sense why you've selected that system, and you have access to that system. That's the key things that I'm trying to get out of this. And then there are some sample input modeling reports from previous semesters on Canvas, as well as some sample final project reports on Canvas as well. Okay. Otherwise, there's more ICAs. Homework H has been posted. There's only one homework after that, homework J2. That's the one that can't be dropped. and will involve some arena. So you know enough right now for question 1 of homework H, and then today we'll cover, and we already covered a little bit of this, but we'll cover what you need for question 2. There's also a video online. If you go to that homework assignment, I kind of walk through the steps that you need to solve homework or question 2. Okay, any questions, comments, worries, anything? Okay, so let's do a quick, early class clicker, multiple choice this time. And so this one has multiple answers. And so either answer is fine. Again, these aren't graded for correctness. But the question here is, I should be most suspicious of blank p-values when I have blank number of samples, where it's either low or high p-values and large or small number of samples, many or few number of samples. So think about that for a second. The pairings here are low p-values and a small number of samples, high p-values and a large number of samples, low p-values and a large number of samples, and high p-values and a small number of samples. What should you be most suspicious of? And I'll let you think about that. And then, so lock in your answers. How many people, I guess I can just look at what the stats are here. So, so far, we've got a pretty uniform distribution. And as a hint, when you have more data, you can always detect very, very small changes, and vice versa. So these have settled out here. Okay, so interesting set of results so far. So there's this mode here at A, and then there's these additional modes here at C and D. Nobody likes B. So something you have to sort of keep in mind here is that, a low p-value, that means that it is very unlikely that the data you have come from your null hypothesis. So a low p-value means you've detected, or you're very close to detecting, a difference from the null expectation, from just the standard everyday average result. So you've detected something interesting. So a low p-value is a detection. So whenever we see low p-values here, what we're really saying is detection. So I should be most suspicious of a detection. That's a low p-value. And so if we think about it, when should we be most suspicious of a detection? Well, like I was just saying, if you have a lot of data, you will eventually be able to detect anything. So if you have a model of human physiology that involves the location of Mars in the solar system at this particular time, or a model of human physiology that does not include Mars, and then you're trying to figure out which one is a better fit for data, eventually you're going to be able to tell the difference that these two models, the one with Mars will probably end up being a better model. Eventually, once you've got enough data, if you monitor human physiology for a long enough period of time, you would start seeing that when Mars is particular spots in the solar system, it has this minuscule, but with enough data, detectable change in human physiology. So, but is that little tiny change actually, important to our stakeholders? And rarely is it. So when you have high amounts of data, then so that's these two things here, or sorry, high amounts of data, that's large. These are these two things here. Then we have to be careful because that's naturally going to drive our p-values down because with enough data, you become very, very sensitive. So if you have very low p-values and high amounts of data, then you might say, well, okay, I've detected a difference, but is it a meaningful difference? So that's one of these cases here is when you have low p-values and large numbers of samples. So C is one of the answers that I was looking for here. These aren't graded for correctness, so I'm hoping to not see these modes suddenly snap into everybody going to C now. But so that's the one case there is that so if you see low p-values, if somebody comes back to you and says, I had a p-value of 0.0 and with 100 zeros behind it, 7. And you should ask them, well, how much data did you have? And so I had, a million independent sample points. And then you say, well, yeah, so of course you've detected a difference with a million sample points. I need to now ask how big of a difference that was. Because just because you've detected a difference doesn't mean it's a meaningful difference. If you find out that, oh, it's actually, it will improve productivity by a half an hour or something like that, like it'll improve wait times by a half an hour, well, that's a meaningful difference. But if you've taken so much data that you've detected a difference between the intervention system and the as-is system, but there's only like a 1 second difference between the waiting times, that's probably not a meaningful difference. So then the other half of that is the other side of the p-values, when you have really high p-values. So when you have really high p-values, your gut might say, oh, I should accept the null hypothesis. In other words, there's no difference from the null. I have not detected a difference from the null. But if you have really high p-values, that can result from just not having a lot of data. Because when you don't have a lot of data, then you can't discriminate. So every hypothesis is going to have a high p-value with very little data. That coin flipping example, if a coin comes up heads twice, you can't really say anything about how fair the coin is because a fair coin will come up twice, heads or tails, very frequently. So having very little data is going to give you very high p-values. So that's the other half of this is that if I have high p-values, I should be, if I have high p-values, I should be most suspicious if I have small numbers of samples. And so that's why, we have tests, which the next question here is going to be about. We have tests like the Kolmogorov Smirnov test, the KS test, that allow us to draw conclusions with small amounts of data. Most tests, if you have small amounts of data, you're just going to get high p-values, but that's just because the test isn't very sensitive. All right, so any questions about that? So I was looking for answers C or D here. So low, large, and high, small. If you have small p-values but high numbers of samples, you might have detected a difference, but it's not a meaningful difference. If you have high p-values but small numbers of samples, those high p-values might just be because you have very little data and so you just can't detect anything. Questions about that? So think about these things as you're using that input analyzer and you're looking at the p-values that are coming out and so on. If you give it a data set that's gigantic and it just keeps rejecting all of these distributions, but those are the only distributions you have. And visually, it looks like one distribution actually is pretty good, but it just keeps coming with a very low p-value. That's probably because that distribution might be the best, that you've got available to you that you can easily implement in Arena, but it does technically have a slight difference from your data, that your data show a small residual, a small error. And you've detected that because you have a whole lot of data. So these p-values are diagnostic tools to help you toward an answer, but they aren't the answer. So don't completely justify your choices when you're picking models by saying, oh, the p-value was less than 0.05. Give me more. Show me the QQ plots, the PP plots. Show me a histogram with the PDF overlaid on top of it. What other evidence do you have to support your conclusion? Okay. So then next one more. All right, so related to some of the things I was just saying there, let's do, this is a short answer. So I'm looking for one word here. All right, so that I think that poll's running. Yes, okay. All right, so question here is a test with higher statistical blank will reject false hypotheses with fewer samples. So there's a term we're starting to use, we're going to use it more today, where we're saying that when you have very little data, but you need to be able to draw a conclusion, what type of test do you need? You need a test with high statistical, and then there's a term we've been starting to use there. So go ahead with that, wait for a few more, and then I'll probably just let us recede into the slides because this will be one of the first slides. So this is just, I've said this term a few times. I said things like the Kolmogorov Smirnov, the KS test. This is a test that's like this. It's a test that if it doesn't reject with a small number of samples, you can trust it. Eventually you get so far that you can't trust any test that doesn't reject. But the KS test is so sensitive that if you give it enough data, it will always reject. So if you give it very little data, then it's able to, if it manages to not reject, you have a lot more confidence that it's actually meaningful. Whereas something like the chi-squared test doesn't have as much of this property. So if you have very little data with a chi-squared test, you're going to get high p-values, but that's just because the test needs more data to be able to draw any conclusions. So it just happens to have very high p-values to start with. Okay. So we'll get an answer to that here in a second. I'm going to hit stop here in about 10 seconds. So about 5 more seconds. All right. Okay, so we'll get to that here in a second. So reviewing what we've been starting to talk about, starting from last time. Remember that, so in this class, and generally in stats, we're going to use the term positive to say that we've detected a deviation from the null. That means we've detected something interesting. The data that we have cannot be explained just by random chance or by the standard model that we have, just the thing that we would normally expect. We've detected a deviation from the norm. That's a positive result. So we refer to a positive, a true positive rate, a false positive rate. That's referring to this idea of detecting a deviation from normal. So we would use alpha, the type 1 error rate, is a way to tell us how much error that we want in terms of how many false positives we get. So a false positive has to do that when the null is true, so when the normal thing is true, how often do you look at the data and say, these data are weird, there must be something different going on here? By the normal, that might mean you have your as-is system and your intervention system. And you want to see, did my intervention, did it make a difference, positive or negative, on the performance there? Well, the null expectation is your intervention system is exactly the same as the as-is system. And detecting a difference is detecting that wait times are larger or smaller for your intervention system. So how often do we look at the data, because we only sampled 10 replications or something like that, and just by chance, we accidentally get that the intervention system is better or worse than the as-is system, when in reality, they're identical and you just had bad luck in your sampling. That's what the type 1 error rate is capturing there. So, if you ask the test to have an alpha equal to 0, it just will not ever detect anything. If you ask the test to have an alpha equal to 1, then it will just always detect something. All right, so that brings us to p-value. So p-value is if we assume the null hypothesis is true. So if we assume the as-is system and the intervention system perform equally well, then what's the probability that we would see the data that we saw from our experiment? That's the p-value, or even weirder data. So that amount, so if you have they're equal, that's kind of in the middle here. And if we're thinking about a two-sample test, or sorry, a two-tailed test, then we're saying we could our intervention system could be doing much better or much worse. And so we say our data says that it's maybe over here, it's this much better. So that we ask the probability, what's the probability that we would get data that is this much better than our system or even better, or the equal amount worse than our as-is system or even worse? That's the p-value. And so if that's nice, is that if you've got a test that calculates p-value, then you've got an easy way to make sure that you can abide by the type 1 error rates. You just threshold the p-value. So if your type 1 error rate is 0.05, then you just threshold the p-value 0.05. So if the p-value comes out to 5% or less, then we say it's pretty safe. We will achieve our type 1 error rate if we say we've detected a difference from null. We've detected that our intervention system is better or worse, or at least different than our as-is system. But then likewise, if it's greater, it's hard to make any conclusions. Because in that case, there may be some support for the null hypothesis, for the idea that the intervention and the as-is are the same. There may be support for that, or you just might not have enough data. If you don't have enough data, then again, there's nothing you can conclude from high p-values. So that's what I'm saying here. All right, so that's p-value and alpha. That's the old stuff. And so now we're going to start talking about power. Any questions about alpha and p-value and this idea of detecting deviations from the null being our positive result? It's a good thing because we want to know if there's deviations. That's why it's positive. Okay. Now we've got the other side of that, type 2 error. This is going to handle this case of the null hypothesis is false, which would mean our two systems are not identical. Sometimes the book will say that the alternative hypothesis is true. So that I'm not going to use that framing that much here, but those are equivalent statements for all intents and purposes for this discussion. So here we're saying, let's assume that there is a difference between our as-is system and our intervention system. Our type 2 error is the probability that we fail to detect that difference. Our type 2 error is that even though the systems in reality are different, that our intervention system generated data close enough to our real system that when we looked at it, we said, well, most likely they're actually identical. How often do we make that error? That's the type 2 error, the beta, probability of not rejecting a false hypothesis. And then that brings us to the answer to that last clicker question, power, statistical power. So we define statistical power as being the complement of beta, the complement of type 2 error. So 1 minus beta gives us our statistical power. If you have an 80% statistical power, you have a 20% type 2 error rate. That's just sort of it. But people, it's just more traditional to talk in terms of statistical power. And statistical power is also known as the sensitivity or the true positive rate. So that's the nice thing with statistical power. Alpha is the false positive rate. Power is the true positive rate. So now we can phrase everything in terms of positives. So we can phrase everything in terms of how often do you detect a difference when it's not there, and how often do you detect a difference when it is there. So the false positive and the true positive rate. And so if we have a high power test, then that means that we can conclude that a high power test means it's so sensitive that a small deviation will be detected. So by that logic, if we don't detect a difference, even with a small amount of data, we can conclude there's probably not a difference. So that's why high power tests are great when you have very little data. Okay, questions about that idea? Power and sensitivity. Okay, so what you're going to do in question 2 of homework, this latest homework H, is a power analysis. And a power analysis helps you determine either one of these two things: the number of samples needed to detect a difference of a specified size, or given that you've already run the experiment and you only could afford a certain number of samples, then what power do you get for those number of samples? And in order to figure either of those things out, you need to know the variability in your data and which test you're going to use. So if you say, I'm going to analyze my data with a t-test, and my data, I did a little pilot study, and I know that my data has this variance in it, then if I know that, I know which test I'm going to use and how variable the data are, I can then combine those two things together to say how many samples I need for a given statistical power, or what power I get for a given number of samples. That's a power analysis, and that's what you're going to do in question 2 of the homework. Okay, any questions about that? And we'll see an example of that here at the end today. Okay, all right, so the other idea, the thing I want you to sort of become familiar with is the ROC curve, as some people call it, the receiver operating curve. I say ROC, other people say ROC. And this, it plots the alpha, the type 1 error rate, against the statistical power or sensitivity. So you've got alpha on the x-axis and 1 minus beta on the y-axis. And what this captures is something that, if you remember from early stats classes, and I'll show this diagram in a future lecture, but if you remember, there's a distribution of data you'd expect from your null and a distribution of data you'd expect from your alternative. And they're often plotted as two bell curves with overlapping tails. That picture generates this plot. And what this is basically saying is, for any statistical test out there, a t-test, a chi-squared test, any machine learning classifier, like those Waymos that are driving around, they are frequently classifying pedestrian, car, and so on. They look out at the world and then they make an inference. That's a car, that's a pedestrian, or whatever. Occasionally they get that wrong. So they think they've detected a car, but instead they detect something else. That's a false positive rate. They use a machine learning algorithm, which is basically a tailored statistical test, which is like a t-test, but been customized for computer vision data. And all of those tests, regardless of what type of classifier it is, have a ROC curve, an ROC curve, where there's a type 1 error rate against a type 2 error rate. And they have this trade-off. If your statistical test is a flip of a coin, so you get data in and you just ignore the data and you flip a coin and say, all right, there's a 50% chance this is a car. Flip a coin, it's a car. And then I get more data in and I ignore the data and I flip a coin and say, oh, now it's a person. If you do that, you will sit on this diagonal line where, in that 50% case, you'll be right here. So you will have an alpha of 50% and a 1 minus beta of 50%. If you change the weight of that coin so that it always comes up heads, then you will be up here at 100% alpha and 100% power. And if you change the weight of that coin so it's always tails, then you'll be down here at 0. So the weight of that coin tells you where you are in this diagonal line. So and in a statistical test, like a chi-squared test, that coin weight is your critical threshold value, your table in the back of the book. That you looking that up, that's determining the weight of your fancy coin. But in that case, your chi-squared coin or your t-test coin, it's actually taking in data. So if your statistical test can't do any better than this diagonal line, it's a crappy statistical test. It's not a good statistical test. You may as well just replace it with a coin flip. But if you have a really good statistical test, then it will trace a line that will go way up here close to this corner and then have a turn and then come over here. It'll look almost like a step where it'll go from this bottom corner in the bottom left to the top left to the top right. That's a good statistical test. So most statistical tests are somewhere in between. Here's 3 statistical tests. These happen to be 3 machine learning classifiers. But again, it works with a t-test, it works with a chi-squared test, with a ks test, all of that. You can plot these for every critical value in the back of the book, and you can sketch out one of these curves. And the farther it gets away from this line, the better of a test it is. So that's what the ROC curve is. It's called receiver operating characteristic, ROC, because they came up with this back before they had computer algorithms to do this stuff. These were, these were soldiers and or Navy men on the back or on in submarines looking at radar screens, and they would see a blip on the radar screen, or they'd listen for sonar, and they'd listen for certain blips, and then they would use what's in their brain to say, that's a submarine, that's a whale, or whatever. And then they would, they would then measure how well different individuals were. And they would then plot every individual on an ROC curve like this one. And people who are really good at that job would have a curve that was bent way up here. People who are really bad at that job, who probably shouldn't be on it, would be close to the random chance line. And so that was the receiver, the radar receiver, the person on the other end of it. Now we use it to judge machines the same way we used to judge people, but it's the same curve. All right, so I just wanted to concentrate on for now, and this will come up later in other lectures, this general shape that you cannot get an improvement in type 1 error without a decrease in statistical power. They are coupled together. It is impossible to get one and not, or to change one and not change the other. So you always have to make that trade-off. Do I want to reduce my type 1 error, or do I want to increase my statistical power? All right, any questions about the ROC curve, the ROC curve? Okay. All right, so from last time we talked about sample means, sample variance, different ways to calculate them. We use those summary statistics to help guide us towards how to parameterize these distributions that we've picked. So like I said, there's different formulas for these different cases. And the major tool that we used to pick these parameters was the maximum likelihood estimation method, the MLE. And so in that case, if you have your desired probability mass function or probability density function, then the idea here is, rather than treating the data as variable and the parameters as fixed, you plug your data in as if they're parameters, and then you solve for the parameters that are most likely to produce those data. And we saw examples of that with the exponential, and we saw that the optimal rate for an exponential is just 1 over the sample mean. So it shows that very often those summary statistics will then show up in these maximum likelihood estimates. So, and then, you can solve for these yourself, but there's tables of these you can look up for a bunch of distributions that are out there. So this is one way that you can find those parameters, and there'd be a justified way of finding these parameters. Now, they can also be fit by tools like ARENA's input analyzer, as you saw in Lab 8. So that's another way to do this, and then hopefully you'll get similar results out of that. Okay, so that was from last time. We also then said, once you've got a good fit, once you've got a family and you fit that family to your data by choosing a certain set of parameters, you now need to evaluate the goodness of fit. You have to evaluate that I know this is the best member of this family for these data, but does it actually look like my data? And the quantitative way you can do that is with the chi-squared test. So you can say, where, if I chucked up all of my outcomes into bins, then how often do I actually see outcomes in those bins? And how often would I expect to see outcomes in those bins if it was the distribution that I picked? And then you compare those things together, compare counts to counts. Whenever you compare counts, a chi-squared test is the first thing that comes to mind. And so this is the same chi-square test we've been doing. The big change here is that the expected counts now have to be calculated from your probability distribution. So from your probability mass function, in the case of a discrete random variable like the Poisson, like on the homework, or probability density function with the integrals underneath the curves, in order to get this here. The other big change is that once you have these expected values for every bin, if any one of your bins has an expected value less than 5, you got to look to the adjacent bins and combine it to create a bigger bin. So your bins don't have to be a uniform size anymore. So you create a bigger bin until you get a bin that has at least 5 in its expected values. And ideally, you want to combine things to maximize the number of bins. So you don't want to do a lot of this aggregation. So if you can figure out a way to, maybe combine to the bin to the left, but not to the right, so that you can maximize your number of bins, then that's ideal. And so, that's what we're saying the goal here. And then we've got this critical value, which has this, which we had before the midterm, but it has this degree of freedom here, this new, which is the number of bins minus 1 minus the number of estimated parameters. So now that you're fitting distributions that have parameters and need to be set, someone might tell you, I want you to fit to this particular distribution with this particular parameter. They tell you that before you even see the data. That's not an estimated parameter, so you don't have to penalize the chi-squared test. But if they just say, I want you to fit a Poisson, I want you to fit an exponential, and they don't tell you what parameter to fit, if you have to then pick that parameter from the data, then in that case, you have to penalize the degrees of freedom in your chi-squared test. And so that's where this comes from here. The number of bins minus 1 minus the number of estimated parameters. There are some weird cases like for a uniform, the boundaries of the uniform, we actually don't penalize that because knowing your choice of boundary doesn't actually allow you to solve for any of the data because they aren't a direct formula of the data. So it's if you picked a parameter as a mathematical formula of the data, then you have to penalize here. But if you've picked a parameter because it looks like this is about the range, so I'm going to use that, then you don't have to penalize this. But almost every parameter, they'll be calculated from the data. And if they're calculated from the data, once you know the parameter, you can back calculate at least one data point. So that's why you lose that degree of freedom. Okay. Any questions about the chi-squared modifications here? Okay. The other modification we had here is to the KS test. Looks just like the KS test we did before the midterm. You sort your data, but then you run your data through the cumulative distribution function, the CDF, of the hypothetical distribution that you're testing against. So the data will be sorted because the CDF is non-decreasing. Once you plug it into the CDF will be sorted. So really all this is doing is it's testing for uniformity in the CDF transformed data. So to test for some other non-uniformity, if you have the CDF, you're just testing for uniformity after you run the data through the hypothetical CDF. And if you get uniformity in this KS test, where the data are now this transformed data, then that means that you're very close to the actual CDF. So if I were to view that a different way, and before I would plot a ramp here, that's how we did it before the midterm. And we would say if we're testing for uniformity, then the CDF we're expecting would be a ramp because the uniform one is a flat boxcar. You integrate under it, you get a ramp. So in this case, what we're actually doing is we're testing for differences from the non-uniform CDF, which could be anything. But so if you have an easier time thinking about it this way, great. But otherwise, you're basically just testing for uniformity after you've run the data through the hypothetical CDF. And then it's just identical to the KS test. There's no parameters estimated here. For this class, we don't cover how to do a KS test with estimated parameters. There are ways to do that. They're just more advanced and they do require some penalty, but it's just kind of beyond the scope of this class. So we always talk about a KS test without these estimated parameters, but regardless, a KS test has high power. So you've very few data points and you still can get an answer that that if you don't detect the difference, you can maybe trust that, that it's probably a good sign that the distribution matches your data. All right, any questions about the modified KS test? Okay. Other two tests is sort of just to know about. There's sometimes you need even higher power. And there is a kind of this is even higher power than the KS test is the Anderson-Darling test or the AD test. I'm not going to go over how to do the Anderson-Darling, but just know that if you hear about it out there, it's just a high-powered version, an even higher-powered version of the KS test. It really focuses on differences in the tails of distributions. So if you have very little data, but you really need to make sure that you've detected differences, especially out in the tails where there's very little data, the AD is a good thing for that. Now, occasionally, as you're doing your statistics, things like the t-test, as we're going to learn about, requires your data to be approximately normal before you can even decide to do a t-test. So before you can do a t-test, you have to test for how well your data are fit to a normal. And so because that comes up so often, people have developed tests that are just for normality that are super high power. And one of them is this Shapiro-Wilk test. So a Shapiro-Wilk test, which I'm not going to go over in this class on how to do, but if you ever need to test for normality, you just look up, Shapiro-Wilk. In fact, it's already going to be built in to any statistical tool you use. Just do a Shapiro-Wilk test. And the Shapiro-Wilk test, again, it's not good for anything else but normality. But for normality, it's extremely high power. So if you have very little data, you want to put it into the t-test. But before you can put it into the t-test, you need to make sure it's normal. You run it through the Shapiro-Wilk. And then that way, if it's highly sensitive, if it comes back and says, oh, these aren't normal, then you know that you need to maybe do something else with them or use a different test other than the t-test. But if it comes back and doesn't detect a difference for normal, then it's safe to put them into the t-test or the ANOVA or any other thing that assumes normality. So high-powered distribution-specific tests. Any questions about that? I just want you to know that these exist. And it's all about power, statistical power and low numbers of samples. Okay. All right, yeah, and then this is also a good thing to think about for your input modeling report. Even if you've done so it might be that the input analyzer has given you a chi-squared result out. It may have given you a KS result out. You might find that the chi-squared is going to have a high value and the KS is going to have a low p-value. And that's just because the KS test is super sensitive. So then you have to decide which one of these do I trust. The chi-squared that couldn't detect a difference, maybe because it was just a low power test, or the KS that did detect a difference, but is really, really high powered. So you have all of that stuff, but as the extra gut check, then it's great to provide a QQ plot and a PP plot. And then so if you give me a QQ plot that looks like this, where you've got these deviations from linearity, then that tells me that, well, regardless of what the stats say, it doesn't really pass the eye test. So it's not really clear that this is a good fit for those. So you might have found the best fit within this family, but this family does not look like a good fit. But if your QQ and your PP are both lines, and your goodness of fit test, like your chi-squared, doesn't detect a difference, then that's a good chance that you've picked a good model. All right, so any questions about that? Pretty clear. It's supposed to help provide convincing things you can do for your input modeling report, and then finally for justification in your final project report. Okay. All right, so so V and V is our kind of topic for today. Want to get through a couple of these definitions and then give you a power analysis example to help you get started on that second part of your homework. All right, so V and V, a topic for today. So, as we know, we've got inputs coming in. They have randomness that gets pushed through your simulator to give you random outputs. If you use bad inputs, you're going to get bad outputs. So, this is that garbage in, garbage out property. So you don't want to put garbage into your model, because if you have a really good model, but you put garbage in, the output's going to be garbage, regardless how good the model is. There's a bunch of things that we need to check. So we need to make sure that we've got a good model here. But once we've even settled on a good model, we need to make sure that we've implemented correctly. And so that brings into this idea of verification. So we have these separate terms, verification and validation, and they all fall under the process of testing. So sometimes people call this T, V, and V, testing, verification, and validation. So the first step here is I wanted to put an exponential into my system, but maybe I accidentally, this like a debugging issue. Like maybe I didn't actually put the right expression in for my exponential random variate generator. Verifying that you've got the right inputs coming into your system, that's the verification piece. That's what we mean by verification. It's debugging. But then there's this other piece, validation. Are the model structure and assumptions correct? Maybe the exponential was just wrong for the system. So verification connects to your code. Validation connects to the real world. So doing V and V is making sure that you've coded it correctly and that you've chosen assumptions and model structure that are a good match for reality. So two sides of things that you will evaluate during testing. And calibration, once you've got a rough model structure that seems to be in the ballpark, the iterative process of going through and updating your parameters to better match the real world, so you get a good surrogate, a good proxy, a good replacement for the real system. That's the process of calibration. So the term calibration that has the word caliber inside it, it's improving the caliber of your model, thus to calibrate your model. All right, so that's what I mean by VV and calibration, TV and V. So summarized here, TV and V, this process here where I've got my real system in my head. I have a conceptual model. I think the real system should have an exponential here, a y-bowl there, and so on. I should have different distributions in different spots. That's my conceptual model. I think it should have this many inputs and this many outputs. My conceptual model of what I think captures all the important parts of the system. And so there's conceptual validation and then there's model verification. So once I have this model, I then build it in Arena. Did I build what's in my head in Arena? That's the verification step. But then once I've got it running in Arena, then I look at the way Arena is running and I look at the real world system. If those don't match, then there's a problem with my conceptual model. And I have to then go back and maybe update my conceptual model. And so that's TV and V. Now, once I've kind of gotten in the ballpark, these are my calibration, where I've got my initial model. Then I keep comparing it to reality. I keep revising my model until eventually I get a model that is close enough. And the close enough gets right to that power analysis that we'll close with here today. All right, so any questions about those terms? Verification versus validation and calibration. Is it clear how all those things relate? And otherwise known as V and V. Okay. So that's just all summarized here. So everything I just said right here. Example. So banking example, this might be like a project, or this might be a similar scale as you might do on your final project. Pardon me. So you have this bank that has drive-throughs coming in here, and you're modeling what's going on at the drive-through here. So you go to the system, you take a look at it, you try to think of what the inputs and the outputs are, and you come up with this. You say, I've got these inputs up here, these random variables. These are my arrival rates. These are my service rates. Then I've got decision variables. These are the things that I can intervene on. So this might be the as-is setup. And I might want to see what happens if I increase the number of tellers? What happens if I increase the number of lines? And so on. So these are the things that I can change in the system and measure the difference in my performance. And then my performance out here. So these are the things that are the difference between one design and another and how well they're doing. So I've got the utilization, how often are the tellers being used? Is 100% of their time? Are they sitting idle 50% of the time? The average delay, so how long does someone wait in the drive-through? And then the maximum line length. And so over a day, what's the longest that bank's line got in that drive-through? So those are the things that I'm measuring there. So again, input variables, model, output variables. So this is my general sketch of my system. I don't know what's in this model yet. This is where your simulation logic would go. So at this point, I'm just interested in the inputs and outputs. So now that I've decided on these, I go to the system and I have to do some input modeling. So I end up taking data on who arrives at the bank, how long they're at the teller, those sorts of things. I probably also measure their output stuff too. Like I might want to measure, and this is important for your input modeling, if they're waiting in line, you might want to measure how long every car is waiting in line, but that is not part of the input. That's an output. The input starts the beginning they reach a teller. That's when the service time starts. That time before that they're waiting, that is wait time. That depends on how busy the system is. But once they arrive to a teller, it's all about the teller. It's not about the rest of the system. So I do my inputs, I can do those, and then I want to say that once I've got the right inputs, how do real and simulated outputs compare when using those similar inputs? So I've got a good input model, and I want to say, how basically did I build a good simulation model? If I did, then when I use the same inputs and this simulation model, I should get outputs in my sim that look like outputs in the real world, if I've done my job correctly. So that's what we want to test statistically. We want to test whether our sim model looks very similar to our real world model. Okay, so we're going to collect these responses and compare to these model responses, collect the real responses and compare to the model responses. We're going to focus that all data is collected in the same period of the day. So if I'm modeling at 1 p.m. to 2 p.m., then I need to make sure I only collect data from 1 p.m. to 2 p.m. And then the stats here. So the null hypothesis is that I got it right. The null hypothesis is that the average value of my sim matches the average value of the real world. So it feels like we're probably going to use a t-test here because I'm comparing means. So two populations, do they have the same mean? Population of output from my computer, population of output from the real world, do they have the same mean? T-test. So I'm going to run a certain number of replications from my simulated model, and I'm going to see, just measure the mean from my real world model. And I'm going to say, my real world mean, that one number, how well does it describe the mean of the population of data from my sim? It's a one sample t-test, as we'll see. So one sample because I'm only estimating this mean, and then I'm just using that mean as a given, as my hypothesis. So we'll see that. So I run 6 replications. Why 6? And so this is really the question of power analysis. Like 6, I might just start with 6, but if I find out that I do a power analysis, and this only gives me 60% power, but I'm told that I need 80% power in order for people to trust my results, then I need to go back and run more sims. And that we're going to kind of get to as we do that power analysis. So for each replication, I am going to do the verification step. So for each replication, I want to make sure that my inputs are what I think they should be. So I'm going to take data on the simulated inputs, not because I care about them relative to the real world. It's that if I simulate exponential interarrivals, I want to then take data on those exponential derivals that are simulated, make sure I actually did that correctly, that it's the right, maybe I used the wrong units. Maybe I thought they were going to be arriving with, once every minute, and it's once every hour. So I need to make sure that I do that verification step, that my inputs are as expected. And then the validation step, I'm going to measure the average delay in the sim and compare it to the average delay in the real world. So I get a table that looks like this. These 2 columns are my inputs. So I'm not going to go through the process of analyzing those. But basically, you could at least do like a histogram of these things. Like, my arrivals per hour, this is supposed to be a Poisson random variable with a certain mean. So if I took a histogram of this thing, does it look like it could be Poisson? That would be, a question to ask there. Likewise, in these service times here, does this match the expected service time distribution? So, you can sort of figure out ways to do that. We're going to focus on the validation side of it. So these are the delays that my sim gave me. Does this distribution of delays, I mean, it's got variability, but does this distribution look like a distribution we get in the real world? That's the question we have here. So we're testing this hypothesis, this Y2, is the mean of this population equal to the mean of the real world population? If it's rejected, we need to calibrate our model. We need to update our model to fix whatever is broken to bring it closer to the real world. All right, so how are we going to do that? I mentioned that we're going to lean on the t-test. The t-test is a tool. It's called the student's t-test. It kind of sounds like it's academic. The reason it's called a student's t-test is that William Henry Gossett, who was, he worked for Guinness Brewing. It'd be interesting, there's this like new, I don't know, it's like a Netflix series about Guinness, and I don't know if they're going to have Gossett. I'm kind of hoping that they will, but so Gossett was basically an industrial engineer for Guinness. Guinness was noticing that whenever they made different batches of their brews, then they would need to make lots of them in order to tell whether they've gone awry. Like if they made a cost-cutting measure, if they screwed up the beer, they would need to make a lot of it in order to figure out if they screwed up that beer. And so Gossett said, let me go talk to the people in the people in biometry, the people in agriculture who are dealing with all these fields, and maybe they've got some statistical insights that we can use. And that really became the beginning of industrial statistics. And so he met with this guy named Pearson. You might have heard about Pearson's R, like R squareds and things like that. And they together came up with this idea of small sample inferences, the t-test. And he came back and he enabled Guinness to be able to say, all right, we only need to do like small batches of beer in order to tell the difference when we've made these changes. We don't have to waste a lot of beer in these tests. And that's enabled by this t-test. And he said, this is a really great innovation. I think this could be something that would benefit the world. Could I publish this? And Guinness said that we agree that we'd love to have you disseminate this, but you have effectively a non-disclosure agreement. And so we're not going to allow you to publish it under a name associated with Guinness, but you can publish it under a pen name. And so he came up with the name Student. And that's where we got Student's t-test, is that there's a way to get out of the contractual obligations he had for Guinness with Guinness's blessing and publish it under a hidden name so no one knew where it came from. And eventually people figured out where it came from. But so that's it. When you hear Student's t-test, it sounds like it's like, something dreamed up for like an AP class in high school that you'll never use again, but they just needed to dumb it down for high school or something. And so, but that's not the case. It's just an arbitrary name, Student. So the Student's t-test, we do use it a lot. It's very influential. All right, so we have Student's t-test. It has this statistic. This statistic, we're going to test the hypothesis that the mean of our simulation data are equal to the mean from the real world. So the mean from the real world is this mu that's up here in the numerator here. And the sample mean from our simulation data is this other part on the numerator. So we're looking at the difference between the sample mean and the real mean. We refer to this as a one sample t-test because there's only one sample mean here. If this was y bar minus z bar, it would be a two sample t-test. So it's how many averages do you put in here? Here we're assuming that mu has been given to us. Someone just says that the real world, they didn't give us real world data, they just gave us the mean. And so we plug the mean in there, but then we do have the data from the sim and we sample that, we create a sample average, and that's the one sample in a one sample t-test. So we have this stat here, which is going to basically measure the difference from the null. And it's going to scale it by how much variation is in the data and how many data points we have. That's the kind of exciting thing about the t-test, is it pulls all of that stuff in, how variable the data is and how little the data you have. And with that, it can make an inference that's much better than before that, when they had to use normal, they used to use a z-test. Before the t-test, everybody uses a z-test. But the only way a z-test would work is if you had lots of data. So this allowed you to use those standard norm kind of tables, but allowed you to now use them in small sample applications. That's was the innovation in the early 1900s that we got with the t-test. Now, in order to make this work, Gossett had to make certain assumptions. He had to say that your data coming out of your experiment, they were all independent. So every run of your experiment had to be independent of the previous run. And then the other critical thing is that all of those data had to come from a normal distribution. This is where that Shapiro-Wilks comes into play. I'm not going to make you do a Shapiro-Wilks in this class. We're going to assume that data are well suited for the t-test in this class for simplicity. But when you get out in the real world, if you start doing this types of stats, you will be expected to do that sort of thing. But if you do a t-test, someone's going to ask you, did you check to see if these were normal before you did the t-test? And that's why we need to know that things like the Shapiro-Wilk exist. Okay, So it has to be normal, and then with this hypothetical mean, and then under those assumptions, then this stat should have a student's t distribution with n-1 degrees of freedom. And so there's basically under the null, we'd expect data to have a certain distribution. And if the data are far from that distribution, we reject the null. That's the idea behind the t-test. Okay, so we're going to do a two-sided t-test. So we care about differences regardless of whether they're on one side or the other. That's almost always the case. You almost never do a one-sided. There are special cases, but in this class, it's always two-sided. And here's how that would look. So we got sample data here. We got our sample standard deviation. That's enough for us to calculate a t-value. We find out, we take that t-value, and then we look in the critical value for the t-test in the back of the book. We're going to use half of our significance level in that because the table in the back of the book is for a one-sided. But like I said, in this class, we always do two-sided. So that means we cut the significance level in half when we look up the critical values in the back of the book. Take the absolute value of this thing, compare it to that critical value. It's bigger than that. So that means that our sim is too far from the real one. So that's a problem. So we go back and so does that clear? So we did a t-test. We detected a difference. We detected a difference between the sim and the real world. So we should not be able to detect a difference between the sim and the real world if it's a good sim. It's a bad sim because we detected a difference. Clear on that? So we have to go back and calibrate the model. We have to go back and update our assumptions of the model. So we gather more data. I'm not going to go through all this in great detail here, but basically there was an assumption that was found to be incorrect. It turns out that you need to know what's going on inside the bank to properly account for the wait times outside the bank. So even though our model was focused on the drive-through, our updated model has to also include the arrival rates of customers going into the inside of the bank, even though we don't care about them for this model. So we do those updates, then we update our stats, we do that same process all over again, and now we get a relatively small t statistic, and that is less than our critical value, so we do not reject the hypothesis. It is possible that our sim is a good fit for the real world. But we don't know that yet until we do a power analysis. And that's the sort of second part of your homework, is to do a power analysis to figure out, are we there? Can we trust a do not reject? And so how do we do that power analysis? We have to know what would be the largest deviation between the sim and the real world that our stakeholder would say, that's a crappy sim, we can't use that. So our stakeholder should come back to us and say, if there's a 5-minute difference between the end of class and when people come in, when there's a 5-minute difference between the sim wait time and the real world wait time, then we're saying that's too big. Then we want the sim to be closer than 5 minutes. So they're going to give you that. They're going to say, at what point is your sim so far away, it may as well be a different system. They give you that, and I give you that in the homework. And then from that, and then we say 80% statistical power, that's just our convention, 5% type 1 error, and then we already have variability because we had to get it in order to calculate this table. We could figure out variability. So with that, we can do this power analysis. And so what you're going to have practice on in the homework is you're going to calculate a so-called effect size. And this effect size is going to be the minimum detectable difference. So that 5 minutes divided by the experienced standard deviation. So what we're basically saying is let's say you say there's a 5-minute standard deviation in my sim results. And the stakeholder says 5 minutes is my critical threshold for like when the sim is too far from the real world. Well, that means it's a 1 SD variation from the distribution that I get out of my sim. And that's what the effect size tells you. It's like, so the numerator is the thing that your stakeholder tells you is how close do your two things have to be? Do your sim and your real world have to be? divide them by the standard deviation of the variation coming out of here, and that gives you this effect size, delta. And with that, you're going to look in the back of the book for these operating characteristic curves, OC curves, which are similar to ROC curves, but they plot something a little different here. So I'm going to zoom in, and this is the last thing that I'm going to cover today. In this OC curve for an alpha of 0.05, effect size is on the x-axis. Probability of accepting H naught, so that's the type 2 error, is on the y-axis. So remember, statistical power is 1 minus that. And these curves are labeled with the number of samples necessary to meet that type 2 error, that statistical power. So let's say I did get an effect size of 1, and I want a beta of 20%. That corresponds to an 80% statistical power. I look to see where those intersect. And that effect size of 1 corresponds, it intersects with 20% on this curve, which is 10 samples. So that tells me that as long as I had 10 replications or more, I can trust my failure to reject. If I did not have 10 samples, then I need to continue to sample and then see what my results are after I've gotten at least 10 samples. That's a power analysis. Any questions about that? If not, then we've already had 2 clickers, so I'm not going to keep you any longer. So we'll see you on Thursday.